vector that is given. What if we want to calculate this distance here, and I'm telling you, you cannot use a formula. In fact, for vectors, if you want to visualize, you should try to prevent yourself from making use of formulas, because formulas can only help you to do a calculation, but never really the process of visualization. So if I don't use formulas, is there any way that I can derive this distance over here? Let's think about it. For distance that we are calculating, this is a scalar quantity, which means that most likely I'm not going to go through purely just the two vectors that is given to me in order for me to calculate a scalar quantity. We need a scalar approach. And to do that, let me introduce you to a very simple but useful geometry, which is actually just a right-angled triangle. If I have a right-angled triangle, if this is a right angle here, if I were to say that the hypotenuse here is r, and if I were to tell you that this angle here is theta, what I want you to first try to do for me is to derive this distance in terms of r and theta. To find this distance, let's say this is x, which means that cosine theta, this is equal to x over r. So x is going to be r cosine theta. So if I can see this portion here as r cosine theta, I'm going to try to apply this here, and hopefully that will help me to do a little bit of visualization. Just a heads up, in order for this triangle to be applied here, we actually need to fulfill three conditions. In fact, this triangle is going to be so useful that we are going to give it a name. Okay, my students has given it a name. My students call it the magic triangle, because this is going to be the triangle that can help me to calculate almost all distances questioned in vectors. You know how effective that will be. So if I were to make use of my magic triangle, I need to make sure that it fulfills three conditions. Let me tell you what are the three conditions. Number one, definitely we need to have a right-angled triangle, which we have here. And second, we need to make sure that the length of the hypotenuse is a known value. So the second one is the hypotenuse. And in our scenario over here, the hypotenuse is in fact known. This is vector A. Vectors is not what I want. What I want is the length of the hypotenuse, which means that if I have vector A, this is modulus of A. I also need the third condition, which is theta. But theta is not just any angle. Theta must be the angle that is between two known vectors, because in this triangle over here, I have two choices. I can either go for this as theta or this as theta. But I'm going to go for this as the angle that I'm going to assign theta to, because this is the angle that is between two known vectors. And the reason is because subsequently I'm going to make use of two different equations that can help me to calculate a lot of different lengths, and that will be the dot product equation and the cross product equation. And for both of the equations, it involves theta, the angle, and this angle is the angle that is between two vectors. You know, that's why I'm selecting this, because this is the angle that is between the two known vectors, which means that using my magic triangle, once all the three conditions are fulfilled, I can say that this is modulus of A cosine theta. And I see a cosine theta, that reminds me of the dot product, because through dot product I will get a cosine theta. So I take the two vectors that I know. Let me execute a dot product, which means that A dot B is going to be modulus of A, modulus of B cosine theta. And from what I can see from the visualization of this distance, the distance is calculated by modulus of A cosine theta. So I'm going to make this a subject, because modulus of B is just another scalar quantity, so I can very easily divide it across the equal sign, which means that modulus of A dot B can be calculated by taking modulus of A cosine theta can be calculated by taking A dot B divided by modulus of B. So if I want to calculate the length of projection, it is going to be this, which can be actually calculated by A dot B divided by modulus of B. And if you are already given the vector A, and if you are given the vector B, you can execute very quickly a dot product, and you can also definitely find the modulus of B. That is why this distance can be then calculated. But at the same time, we do know that for vectors, angles is always in the first quadrant or the second quadrant, which means that cosine of theta can be sometimes positive, sometimes negative. So I'm going to put this overall modulus just to make sure that the distance that I'm calculating is an absolute distance. So I'm going to put a modulus here too. Similarly, we can also make use of the same strategy to calculate this distance, or we can also say it physically as the distance of this point from B. And in order for me to calculate this distance, I am going to make use of our magic triangle again. Because on my magic triangle, if this time I apply sine, if I were to call this as y, that means sine theta is going to be y over r, and y can be expressed as r sine theta, which means that this distance here will be r sine theta, which means that this that is here, since it has fulfilled all the three conditions of the magic triangle, right angle, the length of the hypotenuse, I know there's an angle that I'm able to assign theta to. Here will be modulus of A sine theta. I visualize this distance as a geometry based on the right angle triangle that I know. Then I ask myself, how can I calculate the value for modulus of A sine theta? And to calculate the value of this, let's make use of the cross product. If I were to make use of the cross product, A cross B, this is supposed to be modulus of A, modulus of B, sine theta, and n cap. But this is actually not very useful because this is a vector quantity, this is a vector quantity. So I'm going to modulus the left hand side, which will give me modulus of A cross B. This is modulus of A, modulus of B, sine theta. If you are unfamiliar with this, please take a look at the topical outline again, because we have actually derived this to show us how this can become this. So assuming that we are okay with this, what I want to do is to calculate the value of modulus of A sine theta. And modulus of A sine theta appears in my cross product equation, and making this modulus of A sine theta the subject, and since modulus of B is just a scalar quantity, I'm going to divide this across the equal sign. This will give me modulus of A cross B divided by modulus of B, and this will give me the length that I'm trying to calculate now. And this time, because sine theta, regardless of whether theta is in the first quadrant or the second quadrant, it is always going to be positive, so I don't have to put an overall modulus. Furthermore, this is the place where I'm going to do the calculation. This is the portion of my expression where I'm going to sub A in and B in to do the calculation. It is already always positive and always positive. So this will already give me the shortest possible distance from this point to the vector B. And this is our beginning of how we can visualize distance. Please make sure that you understand this magic triangle. And once we are able to do this, we can move on very safely to the second concept, the second key concept that can help us to understand a large part of vectors. And this second key concept